The force on a magnetic material that is situated in a magnetic field can be determined using the following formula: F equals b squared times a divided by 2 times mu0. In this equation, F represents the force, which is measured in newtons. B stands for the magnetic flux density, with Teslas being the unit of measurement. It denotes the area of the material expressed in square meters. Finally, mu0 symbolizes the vacuum permeability, and it holds a constant value of 4 pi times 10 to the power of negative 7 henries per meter. Before you can apply the formula, it's essential to convert the provided values into the appropriate units conforming to the International System of Units, or C. The magnetic flux density, given as 5 Gauss, needs to be converted to Teslas by multiplying it by 10 to the power of negative 4. Thus, 5 Gauss becomes 5 times 10 to the power of negative 4 Teslas. The area, initially given as 36 inches by 48 inches, must be converted to square meters. To do this, the area in square inches is divided by the conversion factor, resulting in approximately 0.1858 square meters. With the values now in C units, they can be plugged into the formula. The force, F, is calculated as follows: F equals the quantity 5 times 10 to the power of negative 4 squared multiplied by 0.1858, all divided by 2 times 4 pi times 10 to the power of negative 7. After performing the calculation, the force is found to be approximately 0.229 newtons. However, the question requires the force to be expressed in foot-pounds as well. To convert from newtons to foot-pounds, a force in newtons is multiplied by a conversion factor. 1 newton is equivalent to 1 over 4.448 pounds, and 1 meter is equivalent to 1 over 0.3048 feet. Therefore, the force in foot-pounds is calculated by multiplying 0.229 newtons by the conversion factor, which gives approximately 0.164 foot-pounds. In conclusion, based on the calculations, the force exerted on the sheet of steel is approximately 0.164 foot-pounds, or equivalently 0.229 newtons. The formula used allows the determination of the force exerted on a magnetic material within a magnetic field. The magnetic force on a material is influenced by several factors, primarily the magnetic flux density, the area of the material exposed to the field, and the permeability of the space surrounding the material. Firstly, consider the magnetic flux density denoted as B in the formula. This parameter quantifies the strength of the magnetic field. A high magnetic flux density results in a stronger magnetic field, which subsequently leads to a greater force being exerted on the magnetic material. The relationship between magnetic flux density and force is not linear, but rather quadratic, as the force is proportional to the square of the magnetic flux density. This means that even a small increase in the magnetic flux density can result in a significant increase in the force experienced by the material. Secondly, the area of the material denoted as also plays a crucial role. The area refers to the surface area of the magnetic material that is exposed to the magnetic field. A larger area implies that more of the material is interacting with the magnetic field, leading to a greater overall force. The relationship between area and force is linear, meaning that if you double the area, you double the force, assuming the magnetic flux density remains constant. Lastly, the vacuum permeability denoted as mu0 in the formula is a constant that represents the ability of a vacuum to support the formation of a magnetic field. It is a fundamental constant in electromagnetism and is defined as 4 pi times 10 to the power of negative 7 henries per meter. Vacuum permeability affects the magnetic force. It is inversely proportional to the force. This means that if the permeability were to increase, the force would decrease, and vice versa. However, in most practical scenarios, especially when dealing with materials in air or vacuum, the permeability can be considered constant. The formula provided assumes a uniform magnetic field. This means that the magnetic flux density is constant across the entire area of the material. In real-world scenarios, this might not always be the case. The magnetic field may vary depending on the geometry of the source creating the field and the distance from the source. If the magnetic field is non-uniform, the calculation becomes more complex and may require integrating the force over the area of the material. The formula also assumes that the magnetic material is homogeneous, meaning that its magnetic properties are uniform throughout the material. If the material is not homogeneous, the calculation becomes more complex. You may need to consider the magnetic properties of each region of the material separately. In some cases, the magnetic material may affect the magnetic field itself. This is particularly true if the material is highly permeable. In such cases, the magnetic field will be distorted by the presence of the material, and the calculation of the force becomes more complex. You may need to use numerical methods such as finite element analysis to accurately calculate the magnetic field and the force. The formula calculates the force on the magnetic material due to the external magnetic field. However, the magnetic material itself may also have a magnetic moment, which can interact with the external field. This interaction can result in additional forces and torques on the material. The force calculated is a static force, meaning it is the force exerted on the material when it is at rest in the magnetic field. If the material is moving in the magnetic field, there will be additional forces, such as the Lorentz force, acting on the material. When dealing with magnetic forces, it is important to consider safety precautions. Strong magnetic fields can be hazardous to humans and can also damage electronic equipment. It is important to follow proper safety procedures when working with strong magnetic fields. The magnetic flux density is often measured using a Gauss meter or a Tesla meter. These devices use the Hall effect to measure the magnetic field strength. The area of the material can be measured using standard techniques such as using a ruler or a caliper. When calculating the force, it is important to use consistent units. The magnetic flux density should be in Teslas, the area should be in square meters, and the vacuum permeability should be in henries per meter. If you use different units, you will need to convert them to the appropriate units before plugging them into the formula. Understanding magnetic forces is crucial in various applications, ranging from medical imaging, like MRI machines, to designing electrical motors and generators. The principles outlined here provide a foundational understanding for analyzing and predicting the behavior of magnetic materials in magnetic fields. Additional resources like textbooks and online simulations can help provide a better understanding and knowledge of magnetic fields and forces. It is also beneficial to consult with experts in the field when dealing with complex scenarios or critical applications. The formula discussed provides a good approximation, but it relies on certain assumptions. These assumptions include a uniform magnetic field, homogeneous material, and negligible impact of the material on the field. For complex scenarios where these assumptions do not hold, more advanced techniques like finite element analysis are necessary to accurately calculate the forces involved. Finite element analysis involves dividing the problem into smaller, simpler parts and solving the equations numerically. This method can handle non-uniform magnetic fields in homogeneous materials and the interaction between the material and the magnetic field. Another aspect to consider is the temperature dependence of magnetic properties. The permeability of magnetic materials can change with temperature, which can affect the force calculation. In applications involving high temperatures, it is important to take this effect into account. In some cases, the magnetic material may exhibit hysteresis, meaning that its magnetic properties depend on its past magnetic history. This can further complicate the force calculation. The presence of other materials near the magnetic material can also affect the magnetic field and the force. For example, if there are other magnetic materials nearby, they can distort the magnetic field and change the force on the material. Shielding can be used to reduce the effects of external magnetic fields. Magnetic shielding involves surrounding the magnetic material with a material that has high permeability. This material will attract the magnetic field lines and prevent them from reaching the magnetic material. When designing magnetic systems, it is important to consider the mechanical properties of the materials. The forces exerted on the materials can cause stress and strain, which can lead to failure. It is important to choose materials that can withstand the forces involved and to design the system to minimize stress concentrations. In addition to static forces, magnetic fields can also exert dynamic forces on moving objects. These forces are described by the Lorentz force law, which states that the force on a charged particle moving in a magnetic field is proportional to the charge, the velocity of the particle, and the magnetic field strength. Dynamic forces are used in many applications, such as electric motors, magnetic levitation, and particle accelerators. The units of measurement for magnetic quantities can be confusing. It is important to use consistent units and to understand the relationships between different units. The C unit of magnetic flux density is the Tesla, while the CGS unit is the Gauss. 1 Tesla is equal to 10,000 Gauss. The C unit of magnetic field strength is the ampere per meter, while the CGS unit is the oersted. The C unit of magnetic flux is the Weber, while the CGS unit is the Maxwell. When working with magnetic fields, it is important to be aware of the potential hazards. Strong magnetic fields can interfere with electronic devices, such as pacemakers and credit cards. They can also cause metallic objects to be attracted to the field, which can be a safety hazard. It is important to follow proper safety procedures when working with magnetic fields. The calculation of magnetic forces is a complex topic, but it is essential for many engineering and scientific applications. By understanding the principles outlined here, you can gain a better understanding of how magnetic fields interact with matter and how to design systems that utilize magnetic forces. The direction of the magnetic force is also important. The force is a vector quantity, meaning it has both magnitude and direction. The direction of the force is determined by the right-hand rule. If you point your thumb in the direction of the current and your fingers in the direction of the magnetic field, then the force will be in the direction of your palm. In some cases, the magnetic force can be used to levitate objects. Magnetic levitation is the process of suspending an object in the air using magnetic forces. This can be achieved by using superconductors, which are materials that have no electrical resistance. Superconductors can create very strong magnetic fields, which can be used to levitate objects. Magnetic levitation is used in many applications, such as high-speed trains and frictionless bearings. The magnetic force can also be used to create torque. Torque is a twisting force that tends to cause rotation. The torque on a magnetic dipole in a magnetic field is proportional to the magnetic moment of the dipole and the magnetic field strength. Torque is used in many applications, such as electric motors and generators. When designing magnetic systems, it is important to consider the effects of eddy currents. Eddy currents are circulating currents that are induced in a conductor by a changing magnetic field. Eddy currents can cause energy losses and can also create unwanted forces. Eddy currents can be minimized by using laminated cores, which are made up of thin sheets of metal that are insulated from each other. In some cases, the magnetic force can be used to create sound. Magnetostriction is the property of a material that causes it to change shape when it is subjected to a magnetic field. This effect can be used to create sound waves. Magnetostrictive transducers are used in many applications, such as sonar and ultrasonic cleaners. When working with magnetic materials, it is important to be aware of the effects of temperature. The magnetic properties of materials can change with temperature. In some cases, the magnetic properties can be significantly affected by temperature. It is important to choose materials that have stable magnetic properties over the temperature range of interest. The magnetic force can also be used to create heat. Magnetic hysteresis is the property of a material that causes it to dissipate energy when it is subjected to a changing magnetic field. This energy is converted into heat. Magnetic hysteresis is used in many applications, such as induction heating and magnetic refrigeration. When designing magnetic systems, it is important to consider the effects of stray fields. Stray fields are magnetic fields that are not confined to the intended region. Stray fields can interfere with other electronic devices and can also be a safety hazard. Stray fields can be minimized by using magnetic shielding. The magnetic force is a fundamental force of nature that plays a crucial role in many technologies. By understanding the principles outlined here, you can gain a better understanding of how magnetic fields interact with matter and how to design systems that utilize magnetic forces. The interaction between magnetic fields and materials forms the backbone of numerous technologies, and a deeper understanding of these principles enables the development of more efficient and innovative solutions.